So we are using the identities, right? To solve a lot of these. Now, take a look at this first one. You have secant plus 1 equal to tangent x, right? There is no way to solve this. You can't get rid of the 1. You can't get rid of the tangent. There is no identity with just a secant plus a 1, right? All of the Pythagorean identities are with the trig function squared. So you're like, okay, I can't just go to the next problem. I got to do this. Well, if the square is the issue, well, you know what? We can just square both sides. Okay, so why don't we start by squaring both sides here? I square this one. Or maybe, oh, here we go. Okay, and I square this side. So when I square this, I get secant squared x plus 2 times 1 times secant, so 2 secant x plus 1 equal to tangent squared x. Okay? Questions? Now, everything here is in secant, but the tangent is not. However, what is tangent squared equal to? Secant squared x minus 1, right? So go back and look. Oops. Tangent is equal to secant squared x minus 1. So that's what we're going to do, is we're going to substitute there. So nothing changes here. Equal to, so the problem is this is the only thing that's like not a secant, right? So I can change it and it becomes secant squared x minus 1. Now, if you have identical terms on both sides of the equation, they cancel out, right? So secant squared, it's like you can subtract secant squared from both sides. It goes away. So, I basically have 2 secant x plus 1 equal to minus 1. So what I want to do now is minus 1, minus 1. So I have 2 secant x is equal to minus 2. Yes? Divide out the 2's. So secant x is equal to minus 1. Secant is like cosine. Where is it equal to minus 1? At pi. So x is equal to pi. Okay, now, beware. For ones like this, you have to check for extraneous solutions. For this one, you have to check for extraneous solutions because whenever you square both sides of an equation, you have the potential of adding solutions into the problem that would otherwise have not existed, right? Because by squaring both sides, you're kind of getting rid of like all negative parts of a problem. So let's check to see if this works. We go back to the original equation. So I have secant, plug pi in there, plus 1. Is this equal to tangent of pi? Secant of pi is negative 1. Plus 1 is 0. Tangent of pi, 0. So that does work. Okay? Yep.
If it doesn't match,
then it's no solution.
like the answer is no solution.
Correct. Yep.
So, but how do we know when we have to?
Whenever you started by squaring both sides, that's when you should check for extraneous solutions. Okay? So take a look at this one. This is a very similar situation. You have cosine and sine. They're both single terms, so you have to start by squaring both sides. So I get cosine squared x equal to sine squared x minus 2 sine x plus 1. Okay? Cosine squared x, again, what is that?
Sine squared x minus 1.
Other way. 1 minus sine squared x. Okay? it's sine squared x plus cosine squared x equals 1. So cosine squared x is 1 minus sine squared x. Okay, right? Equal to sine squared x minus 2 sine x plus 1. So look, the ones here, they go away, right? Because you could do minus 1, they go away. Now what would I do here? Like minus 1.
Oh,
What would I do now here?
Minus, you factor out the sine.
Minus sine squared x and set it equal to 0. Okay? Or add sine squared x rather. So plus sine squared x plus sine squared x. So now this will be 0 equals 2 sine squared x minus 2 sine x.
Can't you divide it by 2?
Now I can you can divide by 2. You can also factor out 2 sine x, and you get sine x minus what? 1. So now what happens to that 2? Does it make any difference in the problem? No, because you can just divide both sides and it goes away. So essentially here, I have sine of x equal to 0. Here, I have sine x minus 1 equal to 0. So what's x? And 0 and pi. Okay. And then here, sine of x equals 1 at x equals pi over 2. Okay. Do we have to check for extraneous solutions? Yes, we do. So let's go ahead and check for extraneous solutions.
And we have to check 3 times.
Yeah, all 3 of them. So let's do x equals 0. Is cosine of 0 equal to sine of 0 minus 1? Cosine of 0 is what? 1. Sine of 0, 0 minus 1. Okay, that failed. Did I go too fast or am I okay? Okay, let's do x equals pi. Is cosine of pi the same as sine of pi minus 1? Okay, cosine of pi is negative 1. Sine of pi is 0 minus 1. Oh my God, that totally works. Now let's do pi over 2. Cosine of pi over 2, how much is that? 0. Sine of pi over 2, how much is that? 1. Minus 1, that works too. So x equals pi and pi over 2 are the solutions. Huh? It doesn't matter. So, okay, I've taught you well. Let's do it because now both of you guys commented on that. Look at that. It's like I created little monsters. Yeah.
so you only check when you put the first steps
Square.
Mm-hmm.
How do you know like that you need to square in the first place?
Because there's literally nothing else I can do here. I can't factor things out. I can't combine things. I can't use identities because it has to be squared.
If it was like a fraction, then you would, because then you would do like common.
Right.
Like,
Right. Okay. Next. This is a completely different type of problem, but it's probably like my favorite one in this whole unit. That means it's good. You know why it's my favorite one? It's because there is literally 0 work. It's all like understanding and like, you know, conceptual. Okay. So, okay. What is this equal to? Sine x. Remember, this is a, what type of identity is it?
It's the top of the audio.
The positive one?
What are they called? Confunction identities.
Not confunction.
Co-function.
Co-function identity. Cosine, cosecant, cotangent. Sine of x is greater than or equal to root 3 over 2. This is an inequality. We already know that when we have inequalities, the solution isn't one or two numbers, it's a range of numbers. So, sine of x, is it the y values or the x values? Y values. So if I say sine of x is greater than or equal to root 3 over 2, I can also say what region are the y values greater than or equal to root 3 over 2. So, on the unit circle, look at what a perfect circle that is. On the unit circle, okay, this is 0, pi over 2, pi, 3 pi over 2, and then 2 pi, all right? So that's the order that we're going to go. Okay, when I'm here, what's the y value? Okay.
I was thinking that you were already there.
No, I'm here. When I'm here, what's the y value? When I'm here, what's the y value? 1. When I'm here, what's the y value? When I'm here, what's the y value? -1. So I want the angles for which the y value is greater than or equal to root 3 over 2. When I'm here at pi over 6, what's the y value? 1/2. Okay, so is that less than or greater than root 3 over 2? Less than, so I need to go further up, yeah? At what angle will the y value equal root 3 over 2? Pi over 3. At pi over 3, the y value is root 3 over 2. Okay? If I go higher than this, is the y value going to increase or decrease? Increase. Is that the region I want? Yes, that's the region I want. Until where is the y value going to be greater than pi over 3? Right. Root 3 over 2. I mean, so here, 2 pi over 3, it's still root 3 over 2. After that, the y value will be less. Here y is 0, then this entire time y is negative. So the only time that my y value is above this line, it's for all the angles from pi over 3 to 2 pi over 3. So the answer is pi over 3 less than or equal to x less than or equal to 2 pi over 3. Okay, that's it. We want the values of x.
Do you want the other notation or is this notation?
This is good. So now, yes. Okay, so go to section here, this page. What page? This is like the second page of the notes. It's these identities. Cosine pi over 2 minus theta is this. Okay, I'm going to do another example of the one I just did. That's a different one, yeah.
Just confirm it doesn't matter if it's the pi over 2 theta is right? It does.
Yes, it does matter.
Oh, we have to get
Only for the what does it not matter? Only for the cosines does it. And secant. Good. Okay, good. Okay.
Wait, what is it?
Why does it matter for those?
Because then it'll be the negative. So if you have, for example, sine of pi over 2 minus theta, right? But if you have sine of like negative, if you have sine of theta minus pi over 2, that's different.
Oh, because the negative.
Yeah. Okay. Now, here's one other thing. Suppose the question asked, so, this will be like f. Suppose the question asked, sine x is less than or equal to pi over 4. Okay? Now, so sine again is the y value, yeah? Yes? Okay. Where will the y, I'm sorry, not 1, sorry, 1 over root 2. So, where will the y value be 1 over root 2? At pi over 4. Okay? Now, what about from 0 to pi over 4? Is it less than or greater than? Less than. So is that a region that I want?
Yeah.
Yes. So with this, the direction is you always start at the 0 and then you go all the way around to 2 pi. So one region here that I want is 0 to pi over 4. Okay? Now, all of these angles have a y value that is higher than 1 over root 2. At 3 pi over 4, now it's 1 over root 2 again. After this, it'll be less than that, yes? Okay, what about here?
It becomes negative.
It's negative, but does it still fit this category? It's still negative all the way up to here. So how do I write the green region? I say or 3 pi over 4 to what? To 2 pi. Okay? So hang on. What I see on the tests often is a student will figure this diagram out. And then they'll say from 3 pi over 4 to pi over 4. You can't do that, right? Because this is a one direction situation, okay? So you have two distinct regions here. From 0 to pi over 4 and then here. Because look, now that we know how to graph these, if I were to graph this, this is 0, pi over 4. This is one region I want. Until 3 pi over 4, there is nothing. And then another region I want is this until 2 pi. Do you see that? So do you see how these are disjointed regions if you do it on a linear scale? So here too, if you like unwrap this, they're disjointed regions. So you've got to have two separate inequalities. Is that making sense to you guys? Okay, and then also pay attention to if this is like less than or equal to, because then this will change as well, okay?